Okay, so although it's true that if we just put the circuit together and hook it up like this, we'll get an inverter. We, for example, don't know how fast that inverter will work, because that's kind of what's this curve telling us. This is telling us how fast we go to a 0 to a 1 state on the output of this inverter, and we could say the same thing about going from 1 to a 0 level. And it doesn't tell us like how these points, these are fairly important places, how these are like what's a legitimate, at some point, because in a mathematically logical environment, I shouldn't say mathematical logic, in logical math space, you only have 0 and 1 defined. So, okay, you go, that's a 0, that's a 1. But in a voltage space, this point, this VDD, is we've called that a 1, and we've called the 0 volt a 0, but, is 0.9 volts also a 1? Yeah, I think so. Is 0.8 volts a 1? Maybe. 0.7? I don't know. It's kind of getting down. Is it 0.5 volts? That defines the difference between 0 and 1. If that's the case, what if you're at 0.50001 volt and you're just a tiny bit away from a 0, which causes us noise margin, etc. So basically, where I'm getting to is that this switch level definition of this really simple switch level model that we talked about, and we can use to generally see the functionality of all logic, works okay for the functionality, but it doesn't tell us anything about other things about this logic design, which is, the how fast is it running, as you'll see, about what power consumption will have, what kind of loading you'll have to other circuits. So we need to find all those things for sort of real circuit design. So all this brings us to the transistor, because the bottom line is that the transistor, NMOS transistor, is a lot more complicated than this really simple model, and a PMOS transistor is a lot more complicated than this simple model. And so we need to start like digging more into these transistors to really have an understanding of how to design a logic element. All right. So that's kind of giving us the outline of the talk today, the lecture, or at least part of the lecture today, and what how does it relate to the project. Okay, so we have, if you think of it as, we've treated the transistor as an ideal switch. So we basically, if you have I talked about that quite a bit just now, but really a real transistor has a bunch of things. Basically, it's got a current versus voltage characteristic. It's got various capacitances. So, for example, I'll describe. First, I'll tell you guys what we're going to talk about, and then get into the details of it. Is when you look at a transistor at a one layer deeper than the switch, is you think of it as let's look at an NMOS transistor. It's really a 3-terminal device. The 3 terminals are the gate, the drain, and the source. So each, and then you have the current going from drain to source, IDS. So really, when we're looking at a CMOS inverter, what we care about is the relationship between these 3 voltages and this drain current. Those are the real important issues. Right off the bat, the first issue is that we can't even draw in one two-dimensional drawing, we can't represent all the voltage relationships because we have the relative relationship between the gate and the source, and then we have the relative relationship between the drain and the source. And between those two things, so that's called the VGS, V gate source, and then V drain source. And so to represent those on a two-dimensional graph, what we have to do is to hold one of these constant and sweep the other one. So first I don't know if it's first or second or whatever we want to look at. We basically, what we do is we hold one constant, we sweep the other one, and then we step the one we were holding constant, so we get a family of curves. So for example, in this case, if I wanted to draw one of the major transfer functions we're looking at is when we look at VDS versus IDS, and we want to look at how the IDS current changes with different drain source voltages. Well, that's going to have a different value for every gate source voltage. So every gate source voltage will give me a different curve here. And so, for example, this is like a relatively low value of gate source voltage, and then this is a relatively high value of gate source voltage. So all of these will affect the actual sort of transfer function or view of what our logic circuit is going to be doing. So okay, so we need to talk about how a transistor works. And generally where people start is in a MOS capacitor, and you try to understand a MOS capacitor before you try to understand a MOS transistor. And a MOS capacitor is just a gate and the substrate. So there's no source or drain in a MOS capacitor. All you have is you have a basically a MOS obviously stands for metal oxide semiconductor. So let's start with the oxide. So in this case here, the oxide is made out of silicon dioxide, and it looks like this very thin layer in the middle here. So that's your oxide in the MOS. So again, this will be the M, this is the O, and this is the S in semiconductor. So we use, in a typical process, use a polysilicon layer for the gate and the silicon wafer as your semiconductor or body, so-called, in this drawing. So, by the way, polysilicon is what that stands for is, so polysilicon is still silicon, but it's not in crystalline form. So you have the two, you can have silicon in crystalline form. So in crystal form, you can have silicon in completely, crystal form means you have a very, very, very well defined structure for your material. So there's all the atoms are aligned in a certain way, and there's a so-called lattice of atoms that make up your materials. So it's in a crystal. It's like, basically, it's a well-ordered arrangement of these silicon atoms. And then you can have silicon, same atoms, but when they're completely not arranged, it's still a solid. They're still made out of silicon. It's called amorphous, means it does not have a crystalline structure, and there's polysilicon, which means it's not fully crystalline, but it's made out of grains of crystal. And we can get really into the details of that, but anyway, that's where polysilicon comes from. So what polysilicon means, although we're calling it metal, it's still a silicon, it's still a semiconductor. It just typically ends up being a very highly doped semiconductor, which means you can kind of treat it as metal with different work function, etc. We won't go into those details. So just remember that the gate material is actually still silicon, but it's called metal. Traditionally, like when the MOS transistor was initially invented, there was an actual metal layer on top of the silicon dioxide. It gradually got replaced with a polysilicon layer for a bunch of reasons that again I won't get into. But so that's what you'll hear it referred to as polysilicon, or more commonly people just call it poly. But it's a semiconductor, but in the scheme of things for our MOS transistor or MOS capacitor, it's this metal, so-called metal part. And then the semiconductor is just, in this case, is the p-type body. You could have the reverse and have an n-type body, and all the voltages, etc., would get flipped around. So anyway, back to our capacitor here. So basically, a capacitor has two. If I just like draw it in a schematic form, something like this, it just has two nodes. So I don't know if you've got to just call it plus and minus. So we just have two ends we're concerned about. So a p-type material, a p-type body, so-called p-type, means there's an excess of holes in the material, in the semiconductor, and these holes, what they are mobile, positively charged carriers. So they're so-called the holes. So they're all moving around, and they can move around inside the semiconductor pretty freely. And because somebody's doped this into a p-type semiconductor, there's a lot of these positively charged mobile carriers in the material. So if I put a positive voltage, when I have a negative voltage, in the case of a negative voltage on the gate, what I'm doing is I'm dumping negative charges on this gate, on this side of the capacitor, and these negative charges all they're doing is they're attracting these positive charges to them. So all you're doing is you're just, that's it. You're just having negative charges here, you have positive charges here, and the positive charges are coming all the way to the gate. That's when the gate is at a lower voltage than the substrate. When the gate ends up going to a positive voltage up to a certain point, up to this voltage, a voltage called the threshold voltage. So V sub t is the so-called threshold voltage. And voltage, and this is a parameter that's created by sort of the value is by design, is selected by design. So V sub t is it can be like 300 millivolts, it can be 500 millivolts, depends on the doping concentration under the gate. So as you put positive voltages, positive charges on the gate, what you're doing is, because you'll have an electric field here, they'll start repelling the positive charges in the substrate, and because these charges are mobile, they will actually start to physically move away from under the silicon gate. They'll actually leave a space where there are no mobile charges, no mobile positive charges, where under the gate where you've had these guys move away from it. So that's what happens as the voltage goes above zero, but is below the threshold. Now, once you get past a certain voltage, meaning past the point where this region gets large enough, because as you increase this voltage higher and higher, you are making this region that's empty of the positive charge carriers larger and larger. What happens in that region is you're always in room temperature, or above 0 degrees Kelvin. You're always having a generation and recombination of electron hole pairs, and basically electron hole pairs get created and then they recombine and they sort of eliminate each other. So this is constantly happening. Once this region gets big enough, what happens is those electron hole pairs that get generated in this region get separated from each other by the electric field caused by these positive charges. So these positive charges continue to push the holes or the positive mobile carriers away from the gate, but any electrons that get created in this region get pulled towards the gate. So this electric field is separating the electrons from the holes, and once the electrons get separated from the holes, they no longer recombine to sort of end up with like a neutral area, but you end up with an electron rich area right under the gate. So, and that's when you get this process, so you get this thing called so-called thing called an inversion, where the area under the gate is going from a positive value to an inverted or negative value once you put enough voltage on the gate, specifically a voltage above the threshold voltage. And in fact, this threshold voltage is defined by the voltage at which this happens, at the voltage at which you get an inversion of this area underneath the gate. Okay, so that's what a MOS capacitor looks like. Incidentally, when you create this region that's lacking in positive charges, it's called the depletion regions. You're depleting, so first you're depleting this region from positive charges, and then you're inverting this region. So you're going from positive to negative charges. Okay, so what a transistor looks like is you put basically contacts on top of around this MOS capacitor. So if you just look at this region here, it still looks like the MOS capacitor. I have the silicon dioxide gate here, I have the polysilicon gate here, and I have the body here. So, and then what I've basically added to this is a so-called source and a drain. Now notice that this is p-type, means an excess of positive mobile charges. The source and the drain are made from n-type. They're n-type doped. Doping. So meaning that it is a electron-rich area. Now, if you guys remember this, in the absence of, let's say there's no voltages here. Don't think about the voltages to begin with. If this is just sitting by itself, if I just look at that, if I just draw this, it looks like I have a diode. Okay, so if I just draw that, it looks like I have N plus and P type. And this, if I just draw it in a sort of a cartoon structure, it looks like I have a P and an N type, and then the circuit drawing for this looks like a diode. So in fact, that's what I have between the source and the drain. Sorry, the source and the substrate, and also the drain and the substrate. It looks like I have diodes initially. And I have diodes, and if I have my substrate connected to ground, means I've grounded this end of the diode for both source and drain. And as long as my source or drain, which is this part of the diode, so I'm going to call it source or drain, or above the ground value, anything above that voltage, this diode is reverse biased. It's reverse biased, so no current flows, or very little current flows from source or drain into the substrate, or vice versa. There's a barrier that is preventing charges from moving from the source or drain into the substrate. It's just not happening. Okay, so initially, when there is 0 voltage at, now we call the polysilicon the gate. If there's 0 voltage between the gate and the channel, nothing's happening, because like I mentioned, the source and the drain look like completely reverse bias diodes in all directions, so there's no current flowing from source to drain. So in that case, there is no, at VGS is equal to 0, we have no channel. This MOS transistor is in the cutoff region, and there's no drain source current. As I increase the voltage, the gate voltage, so don't look at the gate drain voltage yet, or the gate source voltage necessarily yet, but as I increase the gate source voltage, I am, just like the MOS capacitor, I'm pushing the holes away from the oxide layer, away from my gate, and causing this kind of depleted area around here. So basically, I'm moving these away from this gate, and at some point, as soon as I get to the gate source voltage goes above this threshold voltage, I get sort of you get inversion of the channel, meaning you have electrons here. Okay, so you're no longer, this interface here between source and the substrate, or between the drain and substrate, is still a reverse bias diode, this interface, but because this region is inverted, is full of electrons, this interface is no longer a barrier. So basically now, as soon as this area under the channel gets inverted, under the gate, sorry, gets inverted, I get what's so-called channel. So that's why I'm kind of, sorry, I'm sometimes jumping the gun. So this becomes something called a channel, and now electrons can move from the source or the drain into the channel. And then what happens if you make the gate source voltage a positive voltage? In fact, the electrons start moving from the source towards the drain. So from the source towards the drain through this channel. So you start getting an IDS current. So beginning of current flow. And so what happens is, and then as your increase the voltage between the gate and the source, so sorry, between the drain and the source, you get an increase in the IDS current. So remember that a a resistor. So if you have an increase in voltage of a resistor across a resistor, so you get a current flow across the resistor. So as you get a higher voltage across a resistor, you get a higher current, and that's kind of what is happening in this region when the gate source voltage goes above the threshold voltage and you're increasing your gate source voltage. You get, as you increase your gate source voltage, you get a higher and higher current. So, and that region is called the linear region because IDS, it's not quite linear with VDS, but similar to, it's kind of like a non-linear, it's linear, but I shouldn't say it's linear. Linear is a wrong word because it's not really linear, but it's kind of linear. And we'll talk about the exact equation, okay? And the reason why it's called linear, because it's more linear than what happens after the drain source voltage goes up beyond a certain point. What happens is as you increase the drain source voltage past a certain point, in fact, in our simple model, it's past the gate source voltage minus a VT, minus the same VT, the same threshold voltage that we talked about. Once it gets past that point, you get an effect called pinch off of the channel, meaning that from that point on, as you increase the drain source voltage, you no longer get an increase in current. So if I was going to draw for, let's say, for a VGS value, for if I have, I make the VGS value something and I look at IDS, what happens is initially I get a linear current increase to the drain source voltage, and once I hit this pinch off voltage, I no longer get an increase in IDS. It just stays constant after a certain drain source voltage. So that region is called saturation. So this region is called linear in quotes because it's not really linear, but it's more linear than this region, which is called saturation. So now this is what the roughly what you guys will see in your simulations. So when you are simulating a circuit, that I think what you have is you have an MOS transistor and you're putting a gate source voltage across the gate and source and the drain source voltage across the drain to source. We're connecting the source to the substrate. And what you should be doing for your project is stepping through gate source voltage, and for each gate source voltage, you're sweeping the VDS. So you're going to get a family of curves. So for the NMOS, if you plot VDS versus IDS, for each different VGS, you'll get a different curve. So this is VGS1, VGS2, VGS3, and so VGS3 is bigger than VGS2, which is bigger than VGS1, etc. And basically you get these family of curves of IDS versus VDS, and a similar thing happens for the PMOS, except because it's a PMOS and the substrate's made out of N-type as opposed to P-type, and the source and drains are P plus instead of N plus in the NMOS case, etc. everything is flipped. So basically, your currents are more like going to be running kind of like that for a PMOS. But let's not confuse those two situations. Okay, so that's kind of the curves that you will end up with. So let's see what do I want to say about this stuff. I mean, this is like sort of doing the calculation of all these values, but um, I don't want to sort of get into the doing the proof because it really kind of doesn't really matter. This is a first order estimation, first order model of what happens in a MOS transistor. But this is the bottom line ends up being this summary of in these different regions. So if I have this VDS versus IDS, let's say I have different gate source values. So let me try to explain what happens in these different areas. And the key here is this is a first order model of the transistor. So once you get past the switch, so the reason we call it the first order is this is not the complete explanation of what's going on, but is just a better model than this simple switch model. So this is a first order model, quote unquote, and it's like was the original model of how a NMOS transistor worked. And it's still a pretty good mental model. I still use this to some extent, but we'll talk about how, and as you'll see, the current or voltage characteristics are a little bit different than this. And we'll want to explain why or the different reasons why they're different. Okay, so let's look at these different regions. So let me draw the transistor. So this is for an NMOS. This is V gate, V source, V drain, and the drain source current. So when V gate source is less than, that's the gate to source voltage, is less than the threshold voltage, we're in the cutoff region, so there's no current. So it doesn't matter what VDS, no matter what you do here, there's no IDS. So as long as my gate source voltage is below the threshold, so let's say my threshold, say example, let's say VT is 300 millivolts. So if VGS is less than 300 millivolts, this situation gives me a family of curves all lying on top of each other, all at IDS equal to 0. So this is any VGS less than the threshold voltage. Or in our example, in our example, less than 300 millivolts. They're just sitting on top of each other, and because there is, for all of them, there's 0 current from the drain to source voltage. Once the VGS gets above the threshold value, so this is, and VGS is greater than VT, so this is, you get into this linear region where you get a change in current. So this, you end up with this equation. You get a change in current that's linearly dependent on the gate source voltage you picked, and sort of square law dependent on VDS. That's what I was saying. It's not quite linear. So if I was gonna draw if I was gonna draw you a linear line, it would be like this. The reality is more like, kind of like, well, that wasn't much different. So I'm going to exaggerate. The linearity is, the reality is more like that. So it's kind of not a linear, but it's more linear than the saturation, which is what's happening here. Okay, so in this region, so for each VGS, I will have a different curve. So let's say this is, I'm going to call this VGS is 400 millivolts. This is VGS is 500 millivolts. This is VGS is 600 millivolts. So look at for each different VGS value. As my VGS increases, I get a higher current, I get a higher value here. This is all this region we're talking about yet. We're not talking about this region yet. We're talking about this region, but what happens is for each higher value of VGS, you get a higher current flowing in this region. And then you get this dependence on the VDS. As you notice, as VDS is increasing, my current is going up. Okay. Once you hit this pinch-off region where we talked about this, once you go into the saturation region, that we talked about, that means your drain source voltage goes higher than so-called VDSAT. VDSAT is defined as VGS minus a VT. That means as my VGS is increasing, this value of VDSAT, when I go from linear to threshold, also increases. So this is VDSAT 1, this is VDSAT 2, this is VDSAT 3. At each point, this break of this curve between linear and saturation is here, it's here, it's here. So it's shifting to the top right as I get higher and higher VGSs, because my drain source has to be larger than VGS minus VT to go between linear and the saturation region. Once I hit that, I get this kind of curve. This is the current value for saturation. And notice there's no dependence on VDS here. There's no, where is VDS in this? I don't see it. Meaning that there's a flat line as I'm changing VDS once I'm in saturation. This current is not changing as I change VDS. But it is very strongly dependent on the VGS value. Now it's a square law dependence on VGS minus a VT, the gate source voltage. So it's like a very, this is a square law dependent, is a pretty strong dependence. Okay. So those are that's kind of like the different regions of an NMOS transistor, and you'll see these in your simulations. By the way, beta stands for, this is like a set of parameters, and it's basically the width of the transistor divided by the length of the transistor. So for digital designs, you almost always, like 99.99% of the time, you use the minimum length available to you in the process for the length of the transistor. And basically you're adjusting the width of the transistor to get higher and lower beta values, or essentially higher and lower currents. The other two parameters in this is the mobility of the electron and the oxide capacitance density, or capacitance per unit area. Okay, so for the project one, what you're doing is, again, you're trying to replicate these curves. Depending on your Bronco ID number, you're going to end up with different width transistor. Everybody uses the minimum length transistor, and everybody's using the same mobility times C oxide parameter. That's because you're all using the same process. I forget if it's 45 nanometers or 40 nanometers, whatever it is, it's the same process. And if for that particular process, the electrons will have a certain mobility and a certain gate capacitance density. And as the mobility goes up or the gate capacitance goes up, that depends on the process. You just you're just sort of stuck with whatever process you're designing in. So really, you've want to use the minimum length. You're stuck with these. So really, the only parameter you have to play with is the width of your transistors. And sort of this gives you a certain example again in a pretty older process. And you can see how this is in a 0.6 micron process, and this thickness of oxide, it's a relatively thick oxide. This gives you the dependence on Cox, because that's dependent. Cox is dependent on the 1 over the thickness of the oxide. The mobility is how fast the electrons are moving with respect to the electric field. So if I was going to give you guys the definition of mobility, is that if you have an electric field and you look at the velocity of your electrons, what happens as the electric field gets higher and higher, your velocity gets higher and higher, and this slope is the mobility for, in this case, for electrons, or the mobility of the donors. And then what happens as you hit a certain maximum value at some point, because your mobile carriers are going to start hitting your silicon atoms, this flattens out. But again, that's at a relatively high electric field. We'll talk about that. But before you hit that region, basically mobility is the relationship between the velocity of your carriers and the electric field. And the threshold voltage we mentioned is like something that's designed by the process. So basically you end up, what you do is you calculate beta, which is mu Cox W over L, and you end up with this value for beta. So again, this beta is a function of W over L. You, technically speaking, you as the designer have control over both W and L, but again, if you're doing any kind of digital design, you'll want to keep L at a minimum value and you're adjusting W. And then you basically end up with plots of IDS versus VDS, and you end up like the plots I mentioned. And just to again point out these dependencies, you notice that as VGS is below 700 millivolts, all those curves are basically lying on top of each other at IDS is equal to 0. And as the gate source voltage goes above the threshold voltage, so here VGS minus VT is 300 millivolts, you'll end up with this linear region and then the saturation region, linear region, saturation region, linear region, saturation, linear region, saturation. And you noticed how the break between when you go from linear to saturation is a function of your gate source voltage. As the gate source voltage gets higher and higher, that break point changes, goes to a higher value, and you end up with these kind of curves. So the reason we're plotting this for a 0.6 micron process is because this first order model of the transistor is a lot more accurate for the older processes, and we'll see why that is. But that's kind of good. You see this as like kind of, as you'll see with the, like this probably isn't going to look as nice for your simulation. Your simulations, instead of this going like this and being flat, might look like that, something like that. Actually, it'll look like that, something like that. So, and we'll see why that is. But this is the sort of the first order model of an NMOS transistor. And again, it's a pretty good, although, it's not accurate for a 40 nanometer transistor, I still keep this model in my head because it's still indicative of a lot of things. For example, I know if I want to get double the current for a transistor, I'm going to double the width of the transistor, for example. So that's like a useful, like a model. And I know roughly the point where I'm going to go between the linear operation and the saturation operation is VGS minus VT. So that this is sort of like, these are like very rough ideas that it helps me, mental models that I have. So PMOS, like I mentioned, looks exactly the same. In fact, the IDS versus um, IDS currents for a PMOS look very much like this, with everything kind of flipped. But the main thing I want to talk about, so first of all these, as you'll see in your simulation, all the currents versus your VDSs, you need to go to a negative VDS voltage, meaning that your drain has to be below your source voltage for this current to flow, and your gate source voltage has to be, your gate has to be below your source for the current to flow. So this is what this means, and the direction of the current flow is in the reverse direction to the direction of current flow for an NMOS. But one of the main, so that's one. The other thing that I want that's very important is that typically, so everything is kind of like the same, except if I was going to call this beta N for N MOSFETs, you're going to have something similar here called beta P. So IDS for a PMOS is going to be proportional to beta P, with the voltages thrown in for different voltages. But beta P is mu, the mobility of the holes, because the holes are your carriers in a PMOS transistor, times the capacitance density of a PMOS transistor, times the width of the PMOS transistor over the length of the PMOS transistor. So now you can, again, you're kind of stuck with whatever capacitance you have in your process. You have complete control of the width and length of the transistor. For a PMOS, just like the NMOS, you want to use the minimum length for logic design, and so your tuning knob essentially is the width of the P-type transistor. You want to double the current, you double the width. But also what you have to keep in mind is that, at least in these older processes, and certainly was more true for these older processes than it is now, the mobility of the holes is significantly less than the mobility of the electrons. So mu sub p is less than mu sub n, meaning that for the same width device, so by a factor of 2 or 3 less. So a good rule of thumb is like 2.5x lower. So rule of thumb, let's call it 2x. Rule of thumb is mu sub p is, this is just a rule of thumb. It just really depends on the process. It depends on a lot of things, okay? But let's say mobility of the holes is about half the mobility of the electrons, which means that if you, in the same process, the width of your P transistor is the same as the width of the N transistor, then the IDS current of the P transistor is going to be about half the IDS current of the NMOS transistor. And also, so this is also, again, not a, it's just kind of a rule of thumb. It depends on the process, but it's a good assumption for the most part. And what it means is, when you're doing, as we'll see, what it means is, typically in your circuits, the width of your PMOS transistors are twice as wide as your NMOS transistors. Okay, so that's the current versus voltage characteristic of of these transistors. So let's see how it looks like when I translate this to a actual CMOS inverter. Okay, so if you remember, my circuit looks like this. So I have an NMOS on the bottom and the PMOS on top. And I have V out versus V in, and this is VDD. Okay, so this is gonna get a little complicated. We're gonna go over this a couple of times, but let's look at it sort of a piece at a time here. First go around here, okay? So first notice that here, VN is the gate source voltage for both the NMOS and the gate source voltage for the PMOS because it's shorted together. And the source, this is the source of the PMOS, is on top connected to the drain, to the VDD, to the supply. And here's the source of my NMOS connected to the ground. Meaning what? Meaning that if VN is a high value, my gate source for this guy is going to be a high value. I'm going to turn this guy on. But if Vn is VDD, Vn is equal to VDD. So my gate source voltage for the PMOS is going to be 0. So this PMOS is not going to turn on. I'm going to, with a Vn being VDD, I'm going to turn on my NMOS and my PMOS is going to be off. And then vice versa. Vn is at 0 volts. VGS for this guy is going to be 0 because the gate's going to be at 0, the source is at 0, this guy's going to be off. But if this guy's at 0, the gate source voltage is going to be minus VDD, which is a very large negative voltage, which means that, so if I have a large negative voltage, means that my PMOS is going to be nicely on. So that's what I'm doing, is that's why I have the PMOS stacked on top next to VDD, and I have the NMOS stacked on the bottom next to ground, because that way, with the same voltage on both inputs, I can turn one on and one off, or one on and one off. So that's kind of my goal there. And then notice what happens as you, so that's how you turn these guys on and off. But then also as you transition from on to off, so as Vn goes from, let's say, what happens is if I draw Vn on this axis and V out at this axis, what happens is that at very low values of Vn, so let's say Vn is less than the threshold of the NMOS, the NMOS is going to be off and the PMOS is going to be on. So VDD is connected to my output, so my output in this region is going to be VDD. And then gradually, as this voltage goes higher and higher above the threshold voltage, I'm going to start turning this on. And this is still on, so they're both on at the same time, but the NMOS is starting to turn down on, so it's pulling this node down. So my V out is going to start going drooping down. At some point, as my V in is increasing, so that's what's happening along this line, my V in is increasing, so it means that the VGS of my NMOS is increasing, and the VGS of my PMOS, the absolute value, is decreasing. Means that the NMOS is getting turned on more and more, so it's pulling down the output more and more, and then at some point the output goes to 0 because I'm going to turn off my PMOS. So here Vn is greater than the threshold voltage of my PMOS, the absolute value. Sorry, is less than. So let me put this way at this point. The absolute value of Vn is less than the absolute value of the PMOS threshold. Okay, so you get a curve like this, which looks like an inverter curve, right? At a very low input, I get a high output, and at a high input, I get a high input, I get a low output. So this current characteristics of my IV characteristics gave me this kind of transfer function, so-called. This is a transfer function for an inverter. Now, if I had just switches, if I just had perfect switches here, and if I was gonna superimpose that on this, this is what it would look like. It would be all on, and at some point, the top switch would turn on, the bottom switch would turn off, or vice versa, and you'd get, that wasn't a very good drawing, you would get a perfect kind of, this should be a straight line up and down. So you'd get something like that for a perfect inverter. But instead you have this thing that has this curve area. And this has, this means something for the noise immunity of our circuits.